Imagine an object so dense that a teaspoon of it would outweigh all of humanity. Picture a star's core, more massive than our sun, squeezed into a sphere the size of a city. This is a neutron star, the densest observable matter in the universe. Born from the explosive death of massive stars, neutron stars are cosmic ghosts haunting galactic graveyards. Their gravity and magnetic fields are so extreme they push the boundaries of physics. When a giant star runs out of fuel, it collapses under its own gravity, triggering a supernova. The core is crushed, forcing protons and electrons to merge into neutrons, a sea of matter packed tighter than anything else in the cosmos. Neutron stars aren't quite stars, nor are they black holes. They exist on the razor's edge between the two. They are nature's ultimate experiment in density, a glimpse at matter pushed to its absolute limit. By studying neutron stars, we peer into the universe's most violent events and the laws that govern them. Let's journey into the heart of these cosmic phantoms. We'll witness the death of a star, the birth of its dense remnant, and the mind-bending properties that make neutron stars so extraordinary. This is the story of cosmic life, death, and rebirth, written in the language of extreme physics. The story of a neutron star begins with a massive star at least 8 times heavier than our sun. For millions of years it fuses elements in its core, battling gravity with the energy of nuclear fusion. But this balance is temporary. Massive stars burn through fuel quickly and die young. As the core fuses heavier elements, it eventually creates iron, a dead end, since fusing iron consumes energy instead of releasing it. With no more fuel, gravity wins. The core collapses in less than a second, shrinking from the size of Earth to a city. Temperatures and pressures skyrocket, and the star's outer layers crash down, rebounding in a colossal shockwave. This is a supernova, one of the universe's most powerful explosions. The blast rips the star apart, scattering elements like carbon, oxygen, and iron across space. For a brief moment, the supernova outshines its entire galaxy. These elements become the building blocks for new stars, planets, and life. But the core remains transformed by unimaginable forces. What's left is no ordinary remnant, it's the seed of a neutron star. The next chapter begins deep within this cosmic explosion. In the heart of a supernova, gravity crushes the core until atoms themselves collapse. Electrons are forced into protons, creating neutrons, a process called electron capture. The core becomes a dense soup of neutrons held up by neutron degeneracy pressure, a quantum force that resists further collapse. If the core's mass is below about 3 solar masses, this pressure halts gravity's advance. The result, a neutron star, a sphere of pure neutron matter, just a few kilometers wide but heavier than the sun. Its density is staggering. A sugar cube of neutron star material would outweigh Mount Everest. This is not just a small star, it's a fundamentally new state of matter. If the core were any heavier, not even neutron degeneracy could stop gravity, and a black hole would form. Neutron stars exist on the knife's edge between matter and oblivion. They are cosmic monuments to the battle between gravity and quantum physics. Born from destruction, they are among the universe's most extreme creations. Now let's explore what life would be like on one of these bizarre objects. Imagine standing on a neutron star if you could survive. Gravity here is 200 billion times stronger than Earth's. A marshmallow dropped would hit with the force of 1,000 hydrogen bombs. Anything landing on the surface is instantly flattened into a single layer of atoms. Neutron stars spin at dizzying speeds hundreds of times per second thanks to the conservation of angular momentum. The fastest known spins over 700 times per second, its equator moving at 1/4 the speed of light. Their magnetic fields are 1 trillion times stronger than Earth's, powerful enough to erase credit cards from 100,000 kilometers away. These fields channel particles into beams of radiation, sweeping space like cosmic lighthouses. Newly formed neutron stars are incredibly hot, glowing in X-rays at over 1,000,000 degrees Celsius. The surface is a solid crust of iron, just 1 kilometer thick, beneath which lies a sea of superfluid neutrons. Gravity flattens everything, mountains can't rise higher than 1 millimeter. The result is a world of perfect, terrifying smoothness. The physics here are so extreme they challenge our understanding of matter itself. Neutron stars are not just dense, they are alien worlds governed by the strangest laws in the universe. But how did we first discover these cosmic oddities? The answer lies in a mysterious signal from the stars. In 1967, Jocelyn Bell Burnell detected a strange, regular radio pulse once every 1.33 seconds. At first it was dubbed LGM-1 for Little Green Men, but soon, more signals were found. These were not alien messages but pulsars. spinning neutron stars emitting beams of radio waves. As a neutron star spins, its magnetic poles sweep beams of radiation across space. If one points at Earth, we detect a pulse. The regularity is astonishing. Some pulsars rival atomic clocks in precision. Pulsars are invaluable to astronomers, helping us study space, test Einstein's theories, and even navigate spacecraft. Not all neutron stars are visible as pulsars. Some are too old or their beams miss Earth. But for those we can see, each pulse is a cosmic heartbeat, revealing the extreme physics at play. Pulsars are our window into the hidden world of neutron stars. Their discovery revolutionized astronomy and opened a new era of cosmic exploration. But neutron stars have even stranger relatives. Among neutron stars, magnetars are the most extreme, boasting magnetic fields a quadrillion times stronger than Earth's. These fields are so intense, they can tear atoms apart from 1,000 kilometers away. Magnetars are born from rapidly spinning cores, amplifying their magnetic power to the universe's limit. Their unstable crusts trigger starquakes, unleashing bursts of gamma rays and X-rays that outshine the sun's output in a fraction of a second. Neutron stars can also be cosmic vampires, stealing gas from companion stars in binary systems. This stolen material forms a hot accretion disk, glowing in X-rays, an X-ray binary. Sometimes two neutron stars orbit each other, spiraling closer over billions of years. When they finally collide, they create a kilonova, an explosion forging gold, platinum, and other heavy elements. These collisions are among the most energetic events in the cosmos, shaping the universe's chemistry. Neutron stars are not just relics, they are cosmic engines of creation and destruction. Neutron stars are natural laboratories for extreme physics places we could never recreate on Earth. By observing them, we test the limits of our theories and probe matter at its most compressed. In 2017, LIGO and Virgo detected gravitational waves from a neutron star collision, confirming decades of predictions. This event revealed how kilonovae forge heavy elements and allowed new measurements of the universe's expansion. Each pulse, flare, and wave from a neutron star is a clue to the universe's deepest mysteries. They help us answer what happens to matter at its limit. How are the heaviest elements made? How does gravity behave in the most extreme conditions? Neutron stars are cosmic messengers carrying information from the edge of physics. By studying them, we unlock the operating system of the cosmos itself. And in their story, we find answers to the biggest questions in science. Neutron stars are the universe's punctuation marks, sites of violence, mystery, and creation. The iron in our blood, the gold we treasure, the uranium in reactors, all may have been forged in supernovae or neutron star collisions. We are made of stardust, and some of it is neutron stardust. Studying neutron stars is more than curiosity. It's a quest to understand our origins. Each observation tests the foundations of science, from relativity to quantum mechanics. Neutron stars are eloquent reminders of the universe's strangeness and wonder. They inspire us to keep exploring, questioning, and learning. In every teaspoon of a neutron star lies a story of cosmic creation. And in that story, we find our own place in the universe's grand epic. The cosmos writes its secrets in light, gravity, and matter, and neutron stars are among its most profound sentences.